Hello, everybody. The title of this talk is Boosting Uniformity in Quasi-Random Groups, Fast and Simple. And this is a joint work with Harm Derksen and my former student, Chin Ho Lee. First, an advertisement. I'm writing a book. It's called Mathematics of the Impossible. And you can find the draft on my homepage. Check it out. And now the talk. This talk is about communication complexity in some way. So let's start with the basic two-party setting. There is Alice and Bob. And Alice receives as input a tuple of elements, A1, A2, .at from some group G. And Bob also receives a tuple of elements, B1, B2, .bt from the same group G. And they want to decide if the interleaved group product, that is A1 times B1 times A2 times B2, all the way to AT times BT, is equal to 1, the identity element in the group, or some other fixed element in the group. Now, the communication complexity of this problem depends on the group. So let's first consider the case in which a G is a billion. Then how much communication do you think this needs? Think about it. And in this case, the communication is constant. I allow randomization in the model, so you can just reduce to equality, right? Because if the group is a billion, I can just permute these elements. So I have first the product of the A's, then the product of the B's equal to 1. So Alice and Bob can compute the products in their heads, and they can just essentially check equality of these two. So if G is a billion, this problem is very easy. The communication is constant. Now, what if the group is harder type of group, like a so-called simple groups? And as a hint, here you can encode inner product. Okay, and in this case, the communication becomes linear. So they will need a constant times t. And this looks a strong bound, but if you think about it, it doesn't depend on the size of the group. I can have a super large group, t can be fairly small, a constant compared to the group, and you will get nothing. And the question that was raised with Miles, another former student of mine, was whether you can actually prove the tight bound, which would be a constant times t, the length of the tuple, times the representation size of the group, which is log the size of the group, at least for some group. And this was motivated by some cryptographic application, which I'm not going to discuss now. So some thought was given to this question by various people until in a paper with the Gowers, we proved that the answer is yes for a group like SL2Q. This is the group of 2x2 matrices over the field with the Q element. So for this group, deciding interleaved group products requires communication t times log the size of the group. And our work actually gave bounds either for other groups, even for any simple group, but they were not very strong bounds. So later, Shalev refined some of our other bounds for these other groups. Now, both works, the one with Gowers and the one by Shalev, are somewhat complicated. They use very heavy machinery. And in recent work with Derksen, we actually proved a bound which works for any quasi-random group, G, which is the right class of group. And the proof is really simple. It's really a 3-line proof, which has been called the book proof of this result. And this work generalizes all the previous works, simplifies them, and even improves the parameters quantitatively. So this was the case for two parties. Let's now move to the multi-party setting, and we work in the number on forehead setting by Chandra, Furst, and Lipton. So here the picture only has 3 parties, but in general, I'm going to have K parties, okay, for large K. So here we have Alice, Bob, and Cleo. Each one gets a tuple of elements, okay? And the setup, as you might know, is that Alice has A on the forehead, so she can see B and C, but not A, and so on. So this overlap of information, as is well known, makes this model extremely challenging, extremely powerful, and very useful in a variety of contexts. And this is one of them. So again, they want to solve the interleaved group product, A1, B1, C1, A2, B2, C2, and so on. Before I get to our results, I want to mention that this problem is candidate for solving major open questions. So for example, it could be used for separating deterministic and randomized communication. There was a recent exciting work by Kelly, Lovett, and Mega, but their function is slightly more complicated, and the bounds they get are not quite as good as one might hope. So there is a hope that interleaved group products could give a simpler function with a tight bound. And even more ambitiously, you might hope that these questions remain hard even for a number of parties, which is much larger than log n, which is a well-known barrier in the field. So I'm not aware of any upper bound on this problem, so it's consistent that you can prove a very strong bound for this problem. I think even having an upper bound here would be very interesting because you would need to use some new protocol, which we don't seem to know. Okay, so what was known here? Well, if G is a billion, same story as before. I can predict everything and the communication becomes constant. If G is simple, well, then again, I can reduce this time, generalize in the product to obtain the state-of-the-art bounds in the area, which is the length of the tuple T times something exponentially small in the number of parties. And this is what prevents us from having K, which is too large. And again, the question really for the cryptographic application, the question that we had was to improve the multi-party bounds to take into account the log size of the G factor. And this was done in a subsequent work with Gowers, which was a follow-up to the previous one, which I mentioned, in which we do prove such bounds, but on the negative side, the dependence on K is really bad. It's doubly exponential in K, while we wanted just singly exponential. So actually, this double exponential in K suffices for the crypto application, which was enabled by this result. However, it's still off of the state-of-the-art of T times C to the minus K. So in this work, we achieve indeed the state-of-the-art bound. So we prove a bound which is a T times single exponential in K, and then log the size of the group. This works for any quasi-random group. And this work again generalizes, simplifies, and improves the above works. There is a catch, and that's why you have the star next to simplifies, that the simplification is really striking for groups like SL2Q. The proof is really simple, and you don't need any of the previous machinery. For groups which are not as good for our purposes as SL2Q, you actually will still need the previous work with Gowers to kickstart the process, and then you can use our machinery to get a better bound. Yeah, but if you just want SL2Q, or even groups which are close to SL2Q, in a certain sense, you don't need the previous machinery. So the proof technique is called boosting independence, and it comes from this pure works with Gowers. So let's say that the group is SL2Q, and consider that you have a distribution D, which is over tuples of the group G, so M tuples of G. The lemma that was proved with Gowers is that if D is H uniform, which means that it's a distribution of M tuples, but if you just look at H coordinates, those H coordinates will be uniform over G to the power H. Okay, so if you have such a distribution, if you take sufficiently large but constant a number of independent copies of the distribution, so D1, D2, D100, and you multiply them, or you convolve them, which means you sample from each and you output the component-wise product, then somehow the uniformity increases. So you go from H uniform to H+1 uniform. And this is one of the things which is completely false for abelian groups, right? You can have distribution which will stay exactly H uniform. But the cool thing, and that's why this area is so exciting to me, is that if you go to the non-abelian setting, you increase the uniformity. You go from H to H+1. And somehow, iterating this, you get the communication complexity. The result, I'm not going to say how that's done, but it's not complicated. When the thing becomes sufficiently uniform over the entire space, you're good. The proof of this result was a somewhat technical reduction to the two-party case. And what we do in this work, first we prove a better bound. So we prove that you go from H uniformity to 2 times H uniformity. So this gives an exponential number of savings in the number of iterations, and that's what gives the single exponential bound in K in our work, as opposed to the double exponential bound in K in the Gowers and Viola previous work. And also, second contribution is that the proof is more straightforward and is based on a representation analysis. And I'm going to have a slide on the proof ideas. So again, what we want to show is that if you have a distribution D on G to the power M, so M tuples of the group, if D is H uniform, then if you multiply or convolve a large but constant number of these distributions, you get a distribution which is twice as much uniform, so 2H uniform. And here are the high-level proof steps. So we're going to write the distribution in representation basis. So this is somewhat similar in spirit to the standard Fourier analysis for abelian groups, but now instead of unidimensional, you have higher dimensional matrices. So the representation has dimensions, and the abelian case, again, is the familiar case in which all the dimensions are 1. And if G is quasi-random, then the dimensions are large. So any representation has large dimension. For a group like SL2Q, the representation will actually be a power in the size of the group, which is as good as it gets. In fact, the power here is 1/3, which is optimal. So what do we do now? Here are the 2 steps in the proof. We have the assumption that D is H uniform, and this implies that all the degree H representations vanish. Okay, they will become 0, similar to what you might expect from the abelian case. And the second critical component is that the dimensions of the representations multiply when you are over a product group like this. Okay. You have degree H here, so that means that you multiply representation, you multiply H representations. And this is something where you really use that the group is quasi-random. If it was abelian, you would multiply 1 and would still give you 1, which is now very exciting. Here you multiply something larger, so you get something even larger. Specifically, if you combine 1 and 2, you have that when you multiply two distributions, the new distribution, in some sense, mixes or flattens. A specific norm gets smaller and smaller at a rate which is about the representation dimension of G, which can be very large, as in SL2Q, raised to the power H. Okay, so the rate of flattening is much higher than in the previous work, and this allows us to get to 2H uniform with just a constant number of convolutions. And this is what saves the number of iterations and gives a final result for communication complexity. General message is that representation theory is a very convenient framework. And in fact, in this paper, we give another example. The task is classic. We want to show that any distribution which is close to being H uniform. So if you look at any H coordinates, you'll be close to uniform. It's actually globally close, say in L1 distance, in statistical distance, to a distribution which is exactly H uniform. And this is, as I mentioned, a classic goal, which was started in this paper by Long, Goldjack, Mansour in 2003, where they prove it for the classic case of bits, so Z2 to the power m, so m tuple of bits. Later, Rubinfeld and Xie, they generalized this to groups of the type h to the power m, where h is abelian. So generalize this to any product abelian group. Their proof is somewhat technical, and they have to work in an ad hoc basis to accomplish this. And in this work, we prove a similar result for any product group. So any group G of the form h to the power m, where h can be anything, it can be abelian or non-abelian. And also, our contribution is that we can just work in the plane representation basis, and this actually simplifies the proof even in the case of abelian groups H. And that's the end of the talk. Thank you very much, and I'll see you in Chicago.